So in this video, we're going to be deriving the Underwood equation for the minimum reflux ratio of a distillation column. So what I have here is I have my very top stage. This is my condenser. We have some distillate that's exiting the condenser here at the top, and I have a couple stages here at the bottom. And where I'm going to start is I'm going to make a mass balance that covers this much. It's a little wonky of a rectangle, but it'll work. That covers this area here. So something like this. We have a vapor flow rate. So this is my vapor flow rate. Here is my liquid flow rate. So this vapor flow coming from the stage below. So that's going to have a mole fraction. So yn plus 1 is equal. Well, I'll specify that this is some component I because we might have a multi-component distillation. So that's going to be from stage n plus 1 is going to be equal to the liquid flow rate exiting stage n. So the liquid mole fraction of component I exiting stage n plus the distillate flow rate times the liquid mole fraction of component I from the distillate stage. So this is just a very, very simple mass balance. We have what's entering and we have what's exiting on opposite sides. And so the big assumption that we make with the Underwood equation is that in order to minimize our reflux ratio, we are basically saying that we want minimal reflux. So minimum reflux. And essentially what this means is that as we approach the pinch in a McCabe-Deely diagram, so the area that is bounded between the equilibrium curve and the operating line, so in this case it would be the rectifying section, so it would be bounded by the rectifying line. As we approach the pinch, we are not changing the composition anymore. So minimum reflux composition does not change at the pinch. So essentially what that is telling us is that we have, so our yi from stage n plus 1 is going to be equal to our vapor mole fraction leaving stage n. So these two streams have the same vapor mole composition. And we also know that we can relate this in terms of our partition coefficients, k. So it would be ki times xi leaving stage n. Now, at this point, we have defined our vapor mole fraction leaving stage n plus 1, and we have also defined our liquid mole fraction leaving stage n, and have related that to our vapor mole fraction leaving stage n. So what I'm going to do now is I'm going to rewrite. So essentially, this, I'll use the highlight. This and this are getting redefined. And this are going to be used in this relationship now. So for this relationship, I'll still write down what stage is leaving, but since everything is going to be leaving from the same stage, except for, of course, the distillate, I will stop using this n notation. So we have now a liquid flow rate, and we're going to divide over to this side our partition coefficient. So we get something like yi comma n over ki, and then plus distillate flow rate times our liquid mole fraction of component I leaving the distillate stage. So it is at this point where it makes sense to subtract over this term and pull out our Vyi. So what we have on this side is going to be a 1 because this is exactly what we were pulling out, minus, and we're going to be pulling out a y from the top, but we'll have to divide by our vapor flow rate in order to line up with the operation we are doing here. So this is going to be liquid flow rate over our vapor times I think there is a part that I'm missing here. Well, let's see. So if I pull out the vapor, I get a vapor down here, which relates to our vapor flow rate. And we have this Ki. So the part that I was missing is here. So we have defined something called the relative volatility. And if we have a relative volatility for component I, we are essentially saying that this is the ratio of the partition coefficients for component I versus the heavy key in our distillation. So in order to isolate the partition coefficient for component I, which is present here, we will multiply over to the other side the partition coefficient for a heavy key. So that's the part that I wanted to bring up here. So it's going to be our vapor flow rate times our relative volatility times the partition coefficient of the heavy key. And this obviously is going to be equal to our distillate flow rate times the liquid mole fraction of component I, of course, in the distillate. Now, at this point, I want to get this Vyi isolated by dividing over on both sides. So now I will get something like this. So just copy everything over. Okay, heavy key. And now what will happen in a lot of these kinds of derivations is that we will multiply on the top and bottom this this alpha I, our relative volatility. So now what we're going to see is we're going to get rid of this alpha I term here. So it's going to be D like that. So now this is alpha I minus L over, and I'm going to redefine, actually, I'm going to redefine this much here. So if we multiply this one over here and then this term over here by alpha I, what we're left with is L over V times K heavy key, and we are going to name this term phi. So this, what is left, is just going to be phi. I also forgot, well, for starters, forgot a minus sign there, but also at the top here, we're also going to have that relative volatility term. It is at this point where we would think to do a summation over all components I, because if we do a summation like this, what we end up with is something like how we did in the Ratchford-Rice derivation, where the sum of all of our vapor mole components is going to be 1. So in doing so, we get an equation that looks like this. So V is equal to our distillate flow rate summation over all components I. So I'm going to have, I guess I'll put this first. So I'll have my relative volatility times my liquid mole fraction in the distillate over my relative volatility minus this phi term that we have defined up here. Now this is the Underwood equation for the rectifying section. So this is for the rectifying. And what you could do, much like the Ratchford Rice, is you could go ahead and you could do the same mole balance and the material balance for the stripping section. And what you will end up with is an equation that looks very similar, where we have, instead of V, we have a minus V bar is equal to the bottom's flow rate, summing over all terms I. We have our relative volatility, and this time it's the liquid mole component in the bottoms, and the relative volatility minus this term psi. And psi, in this case, psi is going to be L bar over V bar times K of the heavy key. And so this is the Underwood equation for the stripping section of our distillation column. So here I've outlined an example problem that we can use the Underwood equation for. So these alphas are relative volatilities for 4 components, and this z's that I've coded out here, if I were to do that, you can see that it's equimolar between 4 components, so each of them is 0.25% of the overall mole count in our feed. It's a 50-50 liquid vapor mix, so that our Q is at 0.5. Now, I'm going to go ahead and start defining our Underwood equation. And we're going to give it an input of phi. And what we basically want it to do is we want to return the 0. So it's going to be the 1 minus Q minus the sum of our alphas times our z's over our alphas minus our phi. That's exactly what we derived for the Underwood equation in the rectifying section. And so now let's give it a bunch of phi's that we can use to plot, because I want to plot this out to kind of see where our zeros are and choose a 0 that will make sense for us. So how do I want to go about this? I can choose a range of phi's. So phi's are equal to np.lens space between 0.5 and let's say like 3. Yeah, I think that might work. And I'm gonna give it like 500 spaces. Oh, gotta slip the little thing in there. And now, basically, what I want to do is I want to compile all these values of phi and then plot them out into a graph. So the way I'm going to do that is I'm going to define a new variable called UWs, and this array is going to be equal to our Underwood function with an input of phi for phi and phi's. So these are basically defined variables that we have here. These are linearly spaced, and it's going to return and compile each value for each calculation using the Underwood. So if I were to go ahead and take a look at what that is, we see that we have a bunch of numbers that we can plot. So let's go ahead. Let's initiate a new subplot. And we're going to add the scatter. Config.add scatter. X is going to be equal to our phi's. And then our Y is going to be our Underwoods. Set the mode equal to markers. Let's see what we got. So I think it's just doing a little arithmetic error here because I haven't put proper parentheses around. I also updated my bounds here because it was giving me a divide by zero error. It's not a huge deal, but now that we actually have a proper plot that we can look at, I'm gonna look at what my active phi is. So between my active phi's of 1 and 2, I'm gonna try and find my 0. So we're negative here, and just make the switch to positive right around here. So I'm going to say around 1.385. So I'm going to say that my, what do we call it? Just maybe I'll make a note. So like my phi between active phi's 1 and 2 is 1.385. So we found a solution for one of the phi values that gives us a 0 when we do this zeroing out of our Underwood equation. Now what I've done here is I've just given an example of what might be the output mole values in our distillate. And so in order to get just the mole fraction, we can take each component in our in this array, so xd mole, and then Python is auto finishing that for me. And now these should all be in terms of mole fractions. Very good. So now we can actually use this given phi to find our minimum vapor flow rate. And the way to do that is going back, we see that we have defined what that minimum flow rate should look like, and it's going to be the sum of the sum of this equation essentially. So V is going to be equal to the sum of our alphas times our xd over alphas minus phi. And we're going to be using the solution we found, which was 1.385. Oh, number lock wasn't on. And that gives us a minimum vapor flow rate of around 1.97.